Just have to live with that little seam. Sorry about that. Hello. See a few of you out there. So glad you could be here for uh, week 3. Yeah. So if anybody managed to have any time off yesterday, hopefully you were able to enjoy that. So we're kind of into the long grind of the semester at this point, and just is what it is. Of course, going to college is not always fun. I hope that at least some of the things that we do in this class you find interesting when you encounter them. I do hope that you find in your work with the HLA language that you feel more confident as a programmer, that you can just pick up a new language, and if it has, enough similarities with another type of language that you've worked in, it's pretty easy to get going in it. There are some differences in HLA, and you just have to get used to them. The compiler doesn't always give you the best error messages for hunting down. Oh, good. So Xananaduck says they've been enjoying the programming. So that's good. I actually like it. I think it's neat. I like it even more when we start doing what we're doing this week, which is we start stripping away a little bit some of the layers of high-level programming and actually interact directly with the processor. Yeah, I didn't take Labor Day off either, so I don't know who gets to do that, but maybe somebody does. I had one student I got a message from saying that they were going to get to, so that was lucky for them. I did my normal work, which I know some of you know because some of you were there. Okay, anyway, so again, the semester can feel long. It's 17 weeks. We're in week 3. But hopefully you can stop and sort of linger on those moments when you feel satisfaction, when you feel some sense of accomplishment, when you feel challenged, but not in a way that you feel overwhelmed by it. Okay, so yeah, in chat, there's a question about the move instruction, and we will use the move instruction a lot today. So we'll get to talk about it and consider its implications. So you'll use move over and over and over again, and we'll get to talk about it a whole bunch this week. Okay, so a fair number of people, I didn't count, but a fair number of people, you ended up getting partial credit on some of the week 2 lab because your outputs didn't match the specification. So just remember, as you are working through the module each week, the lab is there. It is written up in some detail. It tells you what the tasks are. It links to guide pages. It links to HLA documentation, and it breaks down the points in terms of how the points are going to be distributed. And then finally, it tells you how to wrap it all up and get it submitted. So I don't think anybody's having a problem with the big picture stuff, but pay attention to those specifications. And remember also that most of the time when I put a requirement in a lab, I do it because I want you to have the experience, or sometimes I do it a little bit because I need it to make my evaluations go smoother for you. So sometimes that's there as a kindness to me when I put one of the requirements in there, because I need certain kinds of outputs to have to more quickly discover what your code is doing and not doing. I'm actually going to demo a couple, so I'm going to switch over to my virtual machine and just I found in the past that people like to see other people's work a little bit. So I'm going to demo 3 week 2 labs. You all know what to expect, but I'll just kind of point out to you what these labs are doing that I thought was just kind of nice touches, or that were kind of, oh, look at this person is really paying attention to what they're doing. So I'm going to switch, get myself in there. I'll just do it right here. Okay, so I got the terminal up. I'm going to open up the editor, and then I'm going to copy and paste some people's stuff in here from my notes. So anyway, I didn't put these people's names directly in here, so you might catch a peek of their names from their documentation. But these three samples from week 2 I picked because they had something that I thought was very nicely done about them. So these are all meant to be compliments of the people who did these things. Don't bother me with that right now. So let me go grab person's stuff. And then we'll go run them. Oh, wait, that's my fault. Yep. I copied and pasted a bit. That's me doing earlier a copy and paste that wasn't correct. What? I don't know what that means. Oh, shoot. It's because I have a Lab 2 folder. Whoops. Okay, here we go. All right, so let's just see what... Okay, so here's one touch that this person did that I liked a lot is it tells me which variable I'm dealing with right now. And I'll also show you how I tested them. So the way I tested them is I put in 1 and 2, and there's the Y. See, and the output looks pretty cool that way. And then this output isn't actually 100% to spec, but it has everything that's important. And just I didn't deduct points because the person didn't put parentheses around the values or anything, which they may have interpreted as placeholders anyway. But this is the required output. The second number, 2, is greater than the first number, 1. Go again. And now I'm dealing with the X, so I'll do them in reverse this time, which should tell me that the first number 2 is greater than the second number 1. That's perfect. And notice again, I liked the outputs here because they are telling me you're dealing with X now and you're dealing with Y now, which I thought was just an extra little piece of information that was helpful to me, the evaluator. The third pass through, I tested the repeat until loops. So I put in an illegal value. And this is nice because I know that it didn't actually accept my X value and it told me that in the output. And then they should be equivalent. So that is a very good piece of work. Good on you. Here's another one. All right, so here's another one that did that same kind of thing. No, that looks like the same code to me. Oh, I see why. Because I didn't call it demo.hla. That's why. There's that paper thing. That's my fault again. Okay, so 1, 2. That is precisely to specification, that output. The thing that stood out to me about this particular implementation is that they took the time to put in a little bit of extra spacing in their outputs, which is just nice. So this person just took that extra little bit of time to put in some extra spacing. They probably ran the program a few times just to kind of look and see what their output looked like. And I think this person has very cool. So notice when I put in a 51, this person says, hey, that's not between 1 and 50, try again. He was the only person who did that, and I thought that was pretty darn cool. So anyway, just a little moment. I'm sure that it didn't take them very long, but just a moment of that little extra attention to the project and what's going on in there that just made it stand out and made it nice for me to evaluate. So good on you for doing that. And then the third one, and then we'll move on. All right, it's demo.hla. Oh, because I did paper again, no doubt. I got something at the top. I don't know why I did that to myself. So this person has this one extra touch, which I thought was cool, which is um, including the word inclusive in their output, which just shows that they took that moment of time to look at that line of code, to think about what it meant, and to add their own little personal touch, like, hey, here's me paying attention and offering this little bit of extra detail, which was super, super cool. And the output, 99% to spec. So, um, so that's how I tested them. And those three, there were other good ones. I just sort of picked out those three because they had some little touch in them that I thought was kind of cool. So, yeah. So there you have it for those. So good work on you folks who I just demoed. That was nice. Um, okay, so there's a question in chat. How do I know which parts I messed up on? So if you go to your lab assignment in Canvas, I put comments there. So you can see my comments to you about what aspect was missing or was done incorrectly, um, is how you can see. If you want the actual sort of all the way down into the details, I can tell you that for people who, there was a 30-point requirement for the three outputs that they be exactly as described on the lab assignment itself. And for people who put outputs that were not anywhere close to that, basically, I took off half. So in other words, instead of taking the entire 30 points away, which is what could have happened because any output that didn't match the requirement was just wrong. But instead of doing that, if people had output that had correct data in it, then I took off half. So you got 15 out of 30 if your issue was the outputs not being to the requirement. And then if there were other things in your code, I will have noted those in the comments. So good question. That's in the that's in Canvas. You can go to your assignment and you can see my feedback on it. Okay, let me switch back over to the browser view. All right, so there's the demos. So let's walk through the module and just make sure everyone's seen it at least once. Hopefully everyone is, but I've had a few sort of communications and comments from people this week that suggest to me that maybe they're not actually reading the content in the module. So it's there for, it's a contract. If you find a mistake, of course, in our contract, which would be a mistake that I have made in any of the module contents, please let me know so that I can correct it. And I'll own that. But yeah, this is effectively a contract about the content that we are covering for the week and where I am drawing my questions from and what the requirements for the lab and the discussion both are. And the nature of our work, which is to be engineers of some sort, most of us, the details matter and precision matters and following the specification matter. So it may frustrate you a bit until you get in good habits of following the specification, but you want to have that habit. I'm certain of it, that it will serve you well. Okay, so anyway, going through the module, this week we are going to talk about registers. You've actually seen one last week, and you even used one last week, but we're going to go into more details about them. Most of these concepts are pretty easy to catch on to. What is a register? What do we mean when we say a register overlay? The eFlags register is going to be a bit hazy for a while because we're not actually going to use it in our code until later in the semester, but it is part of the content, the required content of this class, that we talk about what a register is and what the registers are on our architecture of choice, which is the x86 processor architecture. We're going to continue dealing with binary, hexadecimal, and decimal. So it's important to remember that sort of the native numbering system for us humans is decimal. So we frequently find ourselves thinking in decimal, converting things into decimal, printing things in decimal, so that we understand what it is that we're seeing and dealing with. But the native numbering format of the processor is binary, and hexadecimal is simply a shorthand for binary. So when we say binary, we can interchangeably say hexadecimal because they really mean the same thing. Hexadecimal is just a more compact way of expressing binary. Okay, we've talked a little bit, but maybe we'll repeat it. What we mean by increments of data, and this, what I mean by that is bit, nibble, byte, word, double word, quad word. Well, we'll see most of those things come back up when we talk about registers this week. And then finally, we're going to, in the lab this week, we're going to create a program that does not use variables. It uses only registers. And you'll see what that means when we talk about it. Okay. Oh, there's a question in chat. So if you have a question about my comments on your lab, should you respond as another note on your lab or some other way? So it's easiest for me to find it if after a lab has been graded, you contact me through Canvas inbox. What some people will use the comments on their own lab work for is to leave me a note when they submit their lab. Normally that takes the form of, I never figured out this one part, so I just commented that out, so you know. So they'll leave a note for me so that I'll see it as I'm grading their work and kind of know what to expect if they had a problem somewhere. So if you want some follow-up on the specifics of your grade, it's better to use Canvas Inbox for that. Because I have somewhere on the order of 180 people, and there's no automated thing in Canvas that tells me I've got a note in there. Okay, so that's the first page of the module. The second one is the readings. Some of them you have been brought back to on multiple occasions. The processor register reading in Wikipedia will be new, but these Hello World of assembly and data representation, we've been looking at sections of that over and over and over again. And those are there just to help you get up to speed on the fundamentals here. The fundamentals of data representation, by which we mean the numbering systems, binary, hex, and decimal. The basics of the HLA language. So those are the big ones. And I guess whatever the book covers in terms of the processor specifically. And then I also have linked in here, actually let me bring it up in a separate tab so I can look at it later. Some documentation for the HLA standard library. So we should go in there and look at it today and start to learn how to read it and understand what it's talking about. So once you have a sense of what a register is and what registers we have available to us, the documentation will make a lot more sense. Homework as always. So the lab assignment, there is a starter page as always. So I'm embarrassed to do this. Because we're in a college course. So I apologize to you if you're going to later say, why did he waste our time reading a thing to us that he wrote that we could easily read for ourselves? But it's because of the nature of the kinds of messages I've been getting this week. So a quick view of the lab, since it appears that not everyone reads them carefully. They all have a description, which is generally what it is we're trying to achieve in this lab. Usually there's a link to one or more guides to help you with some aspect of the tasks involved in solving the labs. I have added to every project and lab links to HLA language and library documentation, which was a good idea by one of you in our chat. then a detailed set of instructions. In other words, sort of what do I do from start to finish? Um, Launch a virtual machine, create a lab 3 folder, which I recommend, but you don't obviously have to do. Open a terminal, open a text editor, create a new file, copy and paste some stuff, link to a guide. Complete the requirements detailed below, compile and run the program to ensure it works before you submit it. And then the requirements. So here's where all the points come from. So when I'm writing notes to you, when I'm grading your work, I often won't use precisely the same words, but you should easily be able to read my note and then find in the requirements what I was referring to. But sometimes if there's a big block of points and it'll say like 30 points if you do this thing right, and then I say you didn't do this thing right and you wonder exactly how many points came off, you can always ask me, and I'll tell you how I did the precise detailed math. Normally, I'm trying to award partial credit wherever I can, just to be generous and not make people feel discouraged. So one of the reasons why I don't detail it, if I detailed it, it would be very easy to say you didn't do this right, 0. You didn't do this right, 0. Instead, I just say you didn't do this very well, and then leave it at that, and then take off some partial points for it. Okay. I do make mistakes on math though, so if you do the math and you think I'm not sure if I understand the math, I'm a human, so it may be that I did mess up the math, so you can always ask. All right, so this week has a lot of instructions in it. They are going to need to be read carefully to follow. One thing you will notice though is that nowhere in here does it say anything about variables, because there will not be any variables. So that's why it doesn't reference variables, because there aren't any. It's entirely registers. Oh, and then I forgot the end is, except it won't go back there. And then the last thing says, make sure you submit it, which no one has a problem with that. But anyway, I'm embarrassed to have done that, because I know you could have all read them for yourselves, but I'm just trying to sort of take some of the low-hanging fruit of people who say they don't know, they didn't know any of this stuff. Oh, shoot. No one. Oh, thanks. Now I see it in chat. So what I was just doing, so now I'm less embarrassed because you didn't see me doing it. I was just reading through the lab assignment page, reading through the description, talking about the documentation links I added, the instructions about how to step through the project, the requirements, and then finally submitting the project. And I was just sort of expressing my embarrassment that I'm doing that, because it's written there for you all to see and you didn't need me to do that for you. But I've had some communications this week that suggested to me that not everyone was doing that. So try to lift everyone up, as it were. Okay, the discussion, same issue. So most discussions are probably going to start with here's kind of where to go gather some information to contribute to the discussion. There's going to be an instruction about where to find the instruction. So week 3 filter, this specific discussion. And the issue there is that if you mean to be involving yourself in the class discussion, which is what this assignment is, and you don't actually post your comments and feedback and contributions in the discussion itself, then you're not participating in the discussion. That seems obvious to me, but apparently it's not. So, and again, I'm embarrassed because most of you will think, like, who would this be directed at? It's not directed at most people, but not everyone is reading the instructions. So I'm reading them to you, to very much my own shame that I'm doing that. But anyway, they're all here. If there's anything unclear about them, you can always ask, but they follow the same pattern week after week after week. You find the week, you find the discussion, you contribute to the discussion. When you are posting your own questions, You can put them basically wherever you want, but the best place is just to post a new question, um, and those will pop up for everybody. But the discussion is a discussion, and by that I mean that it involves multiple people in one place discussing one topic. So that's why that is as it is. Um, oh, so someone's asking about their virtual machine in the Lab 2 folder. There was a brief, so there was a moment in the first week when I realized that there was something not right with your virtual machine image. So I went and fixed it. And I uploaded a copy of my own virtual machine in which I had created a Lab 2 folder already. Um, so some of you ended up with an image that already had a Lab 2 folder in it, and that was why that happened. And some of you have the image where I didn't provide you with one and left it up to you to make it. Note that it's not a requirement. It very clearly says it's optional to make those folders. I recommend it, but it's not required. There's no points attached to it. It's just something that I recommend to keep yourself organized so that if ever a question comes up about one of your labs, it's easily found. It's partitioned off from your other labs. That's all. So yeah, some of you ended up with a virtual machine image that had that folder because I had created one, and then I made a clone of my image to share with you. And some of you ended up with one that didn't have the Lab 2 folder. Okay. All right, anyway, so there's the discussion. And again, it's a short set of instructions, but I do expect that you follow them, this being college. Okay, and then finally, reminders, as always, about what we're working on, what week it is. I do intend to look at the individual project one today. I just have to make that happen, so I need to be careful of the time so I don't run crazily over like I did last week. I appreciate those of you who are patient about it. Not everyone was. As it turns out, some people don't like their teacher answering students' questions about the class. Crazy world. Okay, so there's those things. I am going to go back and queue up the lab. But another thing is when I'm giving you tips about how to solve the lab, I'm expecting that you have the capacity to go check the requirements for yourself and that you understand that when I am giving you tips about going about the lab, I'm just giving you tips. I'm not doing the lab. I know how to do the lab already, but I'm trying to give you some help, a little bit of bootstrapping, but it's still on you to read the requirements at the end. Okay, so this is queued up. There's my ranting, which again, apologies to the 80 to 90% of you who didn't and shouldn't have had to hear that, but now it's out there, and now hopefully that at least I have addressed it where everyone can see and hear it. Okay, so let's talk about registers. So there's several things to know about registers, so we'll just kind of build up to it. What is a register? It is memory on the processor itself. And we can actually use that memory as if it were built-in variables in our coding, which is a very cool thing to do. So that's what a register is. It is memory on the processor chip itself. Now, if you think about the memory on a modern computer, there's sort of a hierarchy. There is, and I'm going to simplify the hierarchy by not talking about cache memory. So let's just talk about registers, which are built onto the processor itself. Those are, in a sense, built-in or automatic variables that you always have access to. And because they are on the processor, access to them for reading and writing data is the fastest it can be, because the data doesn't have to move very far across any wires to get to the circuits that will process it. So registers are the fastest kind of memory that there is. The next layer in the hierarchy that we will talk about is RAM, which hopefully everyone knows what RAM is. Random access memory, that part doesn't really matter. RAM is the working memory of your computer. So when you launch a program, when you play a music file, when you do anything that is actively being executed and processed, that will be loaded up into RAM. And the reason why that happens is because that is slightly closer to the processor, and it was engineered to provide efficient access to the data in it. So it's not as fast as registers because it's not on the processor, but if you sort of think about the length of wires and the speed of access, RAM is sort of the next fastest in the hierarchy that we're talking about. So registers super fast, RAM not as super fast, but not super slow. And then finally in the hierarchy we're talking about is the large memory, the static memory, things like hard drives and CDs, which are sort of the furthest away from the processor and not necessarily as optimized for speed of access. So those are the slowest places to store data. But what a computer will do when you launch a program from disk is it will take that program and its data and load it into RAM to get it closer to the processor for faster work. And then as the processor is executing your program from RAM, it will be loading data in and out of the registers to go even faster. So that's kind of the hierarchy. So what we're focused on and what we're only going to use this week is registers. We will not use variables. And when we say a variable in this class, and in fact in any programming, we mean a location in RAM that is being used to store data. So it's less fast than registers. This week we will have no variables, which means that we will not be using RAM in our code. We will only be using the registers, at least directly. Okay, so there's those two bits. I pulled up a few things to look at in terms of pictures and descriptions. So because we're talking about specifically the register set on an x86 processor, and I think this is the picture that I wanted. It is. Okay. Let me make sure you can see it. I can see it. Yeah, so there's a question about why do we have RAM at all? Well, the reason why we have RAM, at least I think why the engineers do it this way, is because the processor itself is mostly consumed with processing circuitry. The circuitry to do logic, the circuitry to do arithmetic, the circuitry to control the flow of information to the various components of the computer system. So there's not much storage space there. So yeah, so they added RAM as to supplement at greater speeds than a hard drive would offer the memory available for storing programs and data for the processor's use. And it does have the advantage, RAM does, that it's modular. It can be expanded depending on your computer system. Of course, this isn't always true, but often RAM can be expanded by adding either bigger or extra chips. We can improve on the technologies of it separately from the work that we do on the processor and so on. So yeah, that's a reasonable observation, Druid, that RAM has some advantages that allow us to sort of address the limitations for storage that the processor has that comes with, because it's not really built for storage ultimately. So yes, that RAM is modular and it's expandable and offers a lot more just pure storage space than the processor can be engineered to offer. Okay. So back to the processor and back to looking at registers. So these are the registers on the Intel family of processors. We are doing 32-bit Intel in this class. If you go look at the registers of a 64-bit Intel processor, you will find that actually these same registers are still there, but they've been expanded to have 64 bits of space and then sort of given new labels on them. Okay, so the table you're seeing at the top are what we call the general purpose registers on the x86 processor. By general purpose, we mean that technically they can be used for whatever purpose a programmer might want to use them for. There are some registers that are hardwired into the processor's circuits that have specific purposes. We will look at one of those today. But these 8 general purpose registers technically would allow us, a programmer, to use them to store and write data based on our own needs. Now you see descriptions next to the labels. So EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. Each of those is a 32-bit memory bank on the processor itself. So that is 8 of 32-bit memory banks. The labels on them, EAX, EBX, ECX, EDX, and so on, those are fixed. So you cannot change those names. If you want to use the EAX register, you will refer to it in your code as EAX. If you want to use the EDX register, you will refer to it in your code as EDX. That can't be altered. It can't be declared. That is hardwired into the processor itself. And by extension, it's hardwired into the HLA language. If you want that particular memory bank on the processor, you will address it as EAX. And then you have a little description to the right. Some of these descriptions are more or less just the traditional uses for these registers, and others of them have sort of become semi-hardwire uses. So EAX, the accumulator, the traditional use of that register, EAX, is to receive the results of arithmetic operations like addition or subtraction. So you add 2 numbers together, you store the result in EAX, you accumulate an arithmetic value as you perform arithmetic into it. That's a traditional use of EAX. It can be used for any other purpose since it's general purpose, but if you look at assembly code written by professional assembly programmers, it's likely that they're going to be favoring EAX for their arithmetic operations when they can. EBX, it says used to address memory or hold data. So EBX is often used. Not everyone in this class will have heard this term or understand what I mean by this, but if you've experienced a pointer in your programming life, EBX, the traditional use of EBX would be to store pointer values, which are addresses, into RAM. And also EBX is just commonly used to store whatever data we need to store there. ECX is often used as a counter, and I suspect simply because of the C. Someone thought, well, I'll just use ECX as a counter. It kind of makes sense. I can remember that. So that's a traditional use of it. We will use it as a counter and for many other things for storing and retrieving data. EDX says the accumulator's backup. For us, it will just be a place where we store data as needed. So for us, EAX, EBX, ECX, and EDX are mostly just kind of used as 4 built-in variables that have 32 bits of capacity on them. In our class, it turns out we will never use the other 4, at least not directly. We could if we wanted to, but we won't ever need to, so we won't. And it will give us a chance to gain some mastery and some sense of understanding of EAX, EBX, ECX, and EDX and the way they are built without introducing 4 more. So there are 4 others. You will see the stack pointer, ESP, and we will talk about what a stack is in Intel assembly and what the stack pointer does later in the semester. So for now, our focus is A, B, C, and D. Okay. And that's why you see it in the notes. We use most A, B, C, and D. In fact, almost exclusively those 4. Okay. So now let's go down to the table lower on the screen, which is trying to, and I'll show you a different picture of this. But EAX has subsections of itself that can be addressed separately from all of EAX. So all of EAX is 32 bits. And I'll show you a different picture here in a second to show you a different view. And let me blow it up. Except for it's not, okay, maybe that's a little bit better. So this whole thing is EAX. All the way from this 31 all the way down to 0. This, if you imagine, there's 32 bits that can be stored in this memory bank. If you go down to the what we would call the lower 16, which is from bit 15 to bit 0, the lower 15 can actually be separately addressed from the entire 32 as AX. So in our code, if we say AX, we're talking about a subsection of EAX, which is this first 16 bits of EAX. Notice, by the way, that the upper 16 bits of EAX are not separately addressable. You can't directly refer to these 16 bits by themselves in your code. You can refer to all 32 bits as EAX. You can refer to this lower. And the reason why we say lower is because what we call the 0 bit is at the far right. So the lower 16 bits you can refer to as AX in your code. And that means I want those 16 bits that are the lower half of the EAX register. You could break it down even further. You can take the top left 8 bits of AX and call those AH in your code and get just these specific 8 bits of this register. So AH is a section of the larger EAX. It's also a section of the larger AX by its nature. And then finally, you can address these lower 8 from bit 0 to bit 7 as AL. These are the low bits, the high bits. So the low bits of A, the high bits of AX. So you can get at various portions of EAX in 4 different ways. All 32 at once, EAX. 0 to 15, those 16 bits as AX. 0 to 7, those 8 as AL. 8 to 15 as AH, those 8. Notice that B, C, and D work the same way. So EBX is 32 bits. BX is 16. The lower 16, and then BL, the lower 8, BH, 8 to 15. C and D also broken down the same way. You'll notice that these other 4 do not break down the same way, but we're not going to worry about that because we're only going to talk about ESP later in the semester. We're not going to really use these other 4 hardly at all. So we want to get some mastery and some understanding of A, B, C, and D. All right, so here's another picture of it. I just got these doing Google. And you can see because Canvas is forcing me to use Microsoft Edge for one of its features, that shouldn't affect you, but for one of my teacher tools, Edge works better than the other browsers do. Anyway, so I did a Bing search. But anyway, in the images, I just brought up the x86 registers, and here's another picture that kind of shows the same breakdown. The lower 16 being AX or BX or CX or DX and so on. And there are many other pictures that you could use that break it down. Except for I can't get them to show. There's one. That sucks. I don't know what that is. I don't want that at all. Those are terrible. There, that's the one I want. Okay, so that's A, B, C, and D. The purpose of the lab this week is to have you have the experience of and thinking about what it means to put data in one of these registers. If I put data in EAX, in a sense, it means I am putting data in AX. And it also means I'm putting data possibly in AH and AL also. And the reverse is often true. So if I put, in fact, it's always true. If I put data in AL specifically, well, because AL is a part of AX, I have then also put data in AX. And because I am putting data in AL, which means I'm putting data in AX, I'm also putting data in EAX, because that's one 32-bit bank of memory with different addressing, with different labels to access different subsets of that 32 bits. Okay, this will be, it's more fun to do in code than it is to talk about it like I'm doing right now. Okay, so we talked about the overlay part. So that's what we mean by overlay, is that AL overlays AX and it overlays EAX. AH overlays AX and overlays EAX. AX overlays EAX. And then EAX is all of it. But they are all part of the same 32 bits and just subsets of those 32 bits. Okay, now the hard one, E flags. So we're just introducing the concept of E flags. You'll get some additional reading support for this, but you should have been exposed to the idea, and then we will actually use the E flags register in our code in coming weeks. But for now, since we're talking about registers, let's talk about this one kind of strange one, E flags. So E flags is not a general purpose register, which means that you do not write data into it when you're programming. E flags has been hardwired into the circuitry of the processor for a specific purpose. And in fact, it turns out for a variety of specific purposes. So let me bring up a picture if I can get the stupid browser to show. There we go. All right, so here is E flags. We're just doing the most basic view of the thing, and then I'll point it out to you when we begin to use it in our code, somewhat indirectly. Okay, before we do that, let's see, there's a question. Are there rules for storing so there's a question in chat. Are there rules for storing data in a 32-bit register? In other words, will the data always be stored on the lowest portion first? I'll bring up the calculator and we'll talk about that, Druid. So I think I can make it clear if we look at the calculator and the implications of storing data in EAX. But yes, when we populate EAX, we are going to populate AL as we're doing that. And then it just depends on the value, but the calculator will probably help. So we'll bring up a calculator here in a sec and look at it that way. Okay, so E flags. Don't get hung up too much on this one. We will actually use it indirectly in our code. This is not a general purpose register. It is a special purpose register. It is hardwired into the processor, which means that as the processor performs operations, the processor is actually writing data to this E flags register. So what you're seeing here is a picture of the E flags register. It is a 32-bit register in our class because we're doing 32-bit Intel. And the reason why it's called flags is because it's actually organized that many of the bits act as Boolean flags on conditions of the processor. So as a simple example, when you subtract one integer from another integer, you can get the result of 0, right? You can say 1 minus 1 equals 0. That's actually something that the processor would recognize as a result, and it would actually flick a switch in the E flags register to note that had happened. That's called the 0 flag. You can see it here kind of on the right half, the ZF 0 flag, and if we locate it in the picture, it's right here. So part of the circuitry of the processor, when it performs something like a subtraction and it gets a result of 0, that circuitry will actually go into that one bit in E flags and flick it on and say that last operation yielded a 0 as a result. And it turns out that we can use that for performing logic, even though you definitely will not have ever seen it, and because you've never seen it, you wouldn't have thought of it that way. But we actually use that in our high-level programming, and we'll use that in our class, and you'll be able to see it. And there are other flags. So the sign flag, as an example, SF here, which is this bit right here. So some parts of the circuitry, when they recognize that a negative value has occurred as the result of an operation, will actually go in and flick that one switch on, saying there's a negative value produced in that last operation. Those hopefully will make some sense. We'll also get to talk about the overflow flag, which is this bit right here. The carry flag, which is the 0 bit. So the point about the flags is it's actually being used to represent a whole bunch of true-false values. And it's being used by the processor when it performs an operation. It will set one or more flags true or false based on the result of that operation. So it's kind of cool. It's something that you would never see in your high-level programming life, but in our class we will actually get to see it, because we will perform operations when we immediately turn around and go look at the flag and see if it's been switched on, which would tell us something about the result. So kind of a cool thing. But for our purposes this week, it's that you have been introduced to the concept of a flags register. All processors have them. And this is what it looks like on the Intel 32-bit x86 processors. Notice, by the way, that not all of the bits are used. So many of the bits are used to represent specific flags, specific true-false conditions, but some of the bits have been just left unused, at least for now, until someone maybe can think of a reason to use them. Okay, so that is the register stuff. I think a lot of this will make more sense when you see it on the calculator and you see it in code. So let me switch and make sure that you can see that I switched this time to the virtual machine. Get logged back in. Confirm that you can see what I see. Okay, so you can do this on your Windows calculator as well. I'm going to use the GNOME calculator that we installed last week, if I can find my way. Yep. So I should be able to go up here and type GNOME calculator. It's this one that's just labeled calculator. Calc was stinky. Galc was kind of stinky. Calculator is the one that we want, which was much nicer for our purposes. So what I would love is to not be dealing in 64 bits, but I don't know that it's going to let me do that. Let me go into preferences and see if... Oh, I can. Haha. So it's calling it word size. Let's not worry about the term, because for us a word is 16 bits. But let's change the word size to 32 bits in the preferences. And now it didn't actually change the display, but you can see that the bits on the bottom are highlighted. So think about these as EAX. So if I put 1 in EAX, and in fact, I'm going to write the instructions that I would use to do this, just in maybe a text file off to the side. Or should I make a program? I think I'm going to make a program. So let me make, how am I doing my folders here? 1 Lab 2 demos. Let me make a folder in here. I'll call it week 3 for myself, and then I'll put stuff in there. And I'm going to do it the way that I would have you do it, which is go into week 3, open a terminal, and then fire up the code editor, and let's do a little program, and then have the calculator as a reference to, it's just consuming more real estate than I want. Get over here a little bit. All right, so let's make ourselves a file. I will call it week3sample.hla. Okay, so This is another one of those things where I'm a little embarrassed to do it, but um, I just know from experience that I would get a comment from someone saying, well, you didn't put comments in your sample. So there. Now I don't have to deal with that issue. Okay, so pretty standard stuff. And we could talk about move while we're at it. Okay, so here's my little week 3 sample. And I'm just going to do a move, and then I'm going to go use the calculator to explore what that move actually means. So I'm just going to do this for starters. Move 1 to EAX. And that's it. Move 1 to EAX. And then we'll look at the calculator to discover kind of what that means. One thing to note here is that HLA will allow you to type EAX in all little letters or in all capital letters. For some reason that just bothers me to put it in all capital letters, but you will not get docked any points for doing all caps for your register names. I just don't prefer it in my own code. So let's talk about move while we're in the process. So what's happening here? Move is just an unfortunately named instruction. So the word we want to use to describe move is that it is an assembly instruction. It is an x86 assembly instruction, and it is arguably the one that you would probably find used the most in most software if you looked at the assembly version of that software. So this is an actual x86 instruction. And it's unfortunately named, and you're just going to have to get used to it. It does not relocate anything. What it does is it copies a value from one place to another. You end up with 2 of that thing, depending on where you copy it from. So what I'm doing here is, in this case, is I am copying the value 1 into the register EAX. Notice also that the move instruction in HLA goes from left to right. So we copy the thing on the left to the thing on the right. So I'm copying the decimal value 1. I know that because there's no % sign and there's no $sign that would tell me that's hex. Move the decimal value 1 into the register EAX. So now let's look at the calculator and ask what would that actually do. In binary, by the way, it would look like this. Let's see, there's a 8, 16. This is what it would look like if I wrote it in binary. 3, 4, 5, 6, 6, 7, 8. Those are interchangeable. I could also do it this way and it would be the same result. So those are all 3 the same. So the sign flag should not go up because there's no negatives happening. But that's a good question. It's a good thing to pay attention to. We're actually going to be, and I'm glad you asked it. So for a while, we're not going to do any signed integers. We're only going to use unsigned values for a while because they work a little bit different at the level of the processor. So we're going to get comfortable with the registers and HLA syntax with unsigned integers for a while. And then at a point, we'll introduce signed integers so that you're ready for the differences in them, and they are slightly different in the way the processor handles them. Okay, so all of these 3 are exactly the same. So in this case, I'm moving what we think of as the decimal value 1 to EAX. In this case, the middle one, I'm moving the decimal value 1 but it's expressed as binary. We know that because of the percent sign. I've separated the nibbles with underscores. Same value though into EAX. And then finally I did it as hex. So the reason I did it in binary here, and I'm going to take the hex off. The reason I did it in binary is because you can kind of see here what's going to happen on the different subsets of EAX. So if we highlight, this is AL. So the act of moving this value to EAX will actually change, we'll actually put a 1 in that 0 bit in AL. It will zero out all the bits in AH. It will put this binary sequence in AX because they're all living in the same memory bank, of course. And then all of the bits across the entire register will look like this. So that would be, and we can see that in binary. In fact, I can change to decimal. I can say, oh, let's you do a decimal 1. And you can see here in the binary display that a 1 goes in there. So let's do something different. Let's touch AH. So this value right here, which in decimal would be 256. So if I were to move 256, which again is copy, I want to copy the value 256 into EAX. What does that cause the processor to store at the processor level? It looks like this. No, this one. Someone may have caught me on that. But we can only change it to 1 in the first 16 zeros, if that makes sense. No. Well, I'll do a couple of examples, Evan, and you can let me know if I've addressed the question after we've done a couple examples, kind of moving around in EAX to see which parts of the register get ones in them. Okay, so 256 in binary, notice we'll zero out AL, and then we'll have this sequence in AH, and then this sort of combined sequences of AH and AL that we could call AX. And then finally, this would be all of EAX. So here's a trick question. It's not a trick, but it requires a little bit of thought. So right now, after this line of code, what would be the value of AL by itself? Which is these, that's 0. Good. Yeah, you guys are on it. So Evan Andrew had got that right. If I look at AL only, that looks like 0. Here's a trickier one. What about AH by itself? One is correct. So AH by itself is these 8 bits alone, which if you just take those 8 bits by themselves will look like 1. What about AX? Nice. Yeah. So 256 was a good gut instinct. The correct one, Evan and D. Hawkins. AH by itself would be 1. What about AX? Which seems trickier than the other two, actually. So here's AX. Nice one, Isnam. Yes, it's 256. So that's right. So this is, if you just interpret these 16 bits by themselves, you get a 1 times 2 to the 9th, which is 256. Nice, Druid. Good one. So, yeah, it turns out that AX is going to look like 256, just like EAX does. So, the observation that this can start to feel more confusing for a while than less is a true one. It can start to feel more confusing than less confusing for a while. So I find it helpful. Two things help me a lot with this. One of them is to kind of just type out, even though it's a huge pain in my rear to do so, to type out the binary in HLA, which I'm allowed to do. HLA will understand it. And then I can see the bits and I can stop and kind of think and I can highlight the bits. That's one of my tricks that I like. The other trick that I like is that I fire up a calculator and I can look around a little bit and kind of get an understanding of what the bits maybe are supposed to mean. The other thing you can do, at least on this calculator, is you can change in the preferences. You can change the word size all the way down to 8 bits if you want to. Which is really now only allowing you to use what would be AL, or in the B register BL, or in the C register CL, or in the D register DL. And you can start to understand, for example, let me clear. Where's clear? Clear the thing. Is this clear? C is C. Oh, because that's hex. Where's the clear? I would like to clear now. Undo? No, I didn't want that. That undid my preference. No, it didn't. Whatever. Okay, anyway, so if you have the GNOME calculator installed, that was done in last week's lecture, you can actually switch the word size around so that the calculator will only let you use 8 or 16 or 32 bits at a time, which can help. I wish I could figure it out. Yeah, I don't know how to clear this stupid calculator. Oh, well, have your way, calculator, I guess. Oh, you can change the bits down here in the lower right, too. I didn't see that before. Control escape. Wait, let me get in the calculator. Now it takes me to the desktop. Okay, anyway, you can begin to experiment, though. You can flick the bits on and off, and you can kind of see, like, what if I fill all the bits of AL? What would that value be? 255, as it turns out. And if now I expand to 16 bits, does that change anything? It does not. That's still 255. If you do the binary conversion, 1 times 2 to the 0, 1 times 2 to the first, 1 times 2 squared, and so on. It also doesn't change it if I go up to 32 bits. It's still 255. So anyway, those are my things that I like to do to get a better understanding, is to use the calculator in programmer mode. You can find these online as well. And also write code where I use the raw binary. So we'll do some more experiments and kind of quiz ourselves a little bit. We're doing pretty good on time, I think. So I want to leave time to look at the first project today and also to offer some tips for the lab. So let's print this out and see what happens. So I'm going to go, what is this? Okay, let's close that. All right, anyway, let's go compile it and see what happens. Okay, so something funny looking is going on here. And this is, I think I put it in my notes. I hope I put it in my notes. I did. So in the HLA section of my notes, you'll see the note that says registers and raw data types. So when you print a register, it comes out in hex. And you can tell that because in decimal, you wouldn't print 0, 1, you just print a 1. And you'd print 0 and not 0, 0. So HLA, when you just print your raw registers, is going to print hexadecimal. That's its default behavior. I'll show you how to override it. Wrong thing. So these are all hex. The other way I know that is because AL is 8 bits, which is 2 nibbles, which is 2 hex digits. AH is 8 bits, which is 2 nibbles, which is 2 hex digits. AX is 16 bits, which is 4 nibbles, which is 4 hex digits. And then finally EAX, which is 32 bits, which is 8 nibbles, which is 8 hex digits. So these are not decimal, and we need to be careful about that. So what I do and what I want you to do in your code, when you are printing raw registers, put the $ in your output so that your user sitting at the screen never has a moment of confusion of what in the heck just happened. They will see the $ on the screen, and then your user will know, oh, this is hex. I get it. This is 00 in hex, 01 in hex, and so on. All right, while we're on that, let's go ahead and follow up with a second thought about that. So if you just output a register in HLA, you're going to get hex. And your code should put $ in your output so that it's very clear what the hex values are. If you want to, you could even label them. I'll show you what I mean by that here by running one. So you could also just put the word hex next to it, and then there's like no question anymore. Oh, $00, that's a hex view of that value. Okay, so there's a question. So if you have the value 10101010, is that 4 bits of data stored or 8? That is 8 bits of data, Druid Dread. In fact, I'll do that one as an example here. So, and in fact, let's not use the calculator. Let's use code to figure out what it is. So Druid's question is, what if I did this? What if I move, let's see, 1010, 1010, 2, I'm going to quiz you guys here, to a register. How many bits of data are stored? The answer will be 8 bits of data stored because it's 8 bits of information. So here I think Druid is where you're about to have a big moment because you're going to see how they connect up with each other. The trick is, as the programmer, I have to say an 8-bit location. So if I want 8 bits, I have to specify an 8-bit destination. So what would be appropriate destinations on the processor for my 8-bit value? And you can pick any of the ones that we've talked about. We have 8 to choose from, as it turns out. AL is one, so a good one, Evan. So here, Druid is kind of where those bits connect up with each other. If you are specifying 8 bits to store, you must specify an 8-bit destination. HLA will give you an error if you try to take 8 bits and store it anywhere where 8 bits won't fit. If you have 16 bits, you must supply a 16-bit destination, and if you have 32 bits, you must supply a 32-bit destination. So yes, so Islam asks, would BL, CL, and DL work as well? And the answer is yes, it would. So I could have used BL here, or CL, or DL. There's actually 4 more while we're on that. What are the other 4 8-bit destinations I could have chosen from? So AL, BL, CL, and DL all would work for these 8 bits because the amount of data being stored matches the destination where they're being stored. Nice one. So a good one, Druid. So I could also use AH, that's an 8-bit destination, or BH, also 8 bits, or CH, or DH. And then if I'm doing those, I just need to remember, like if I write 8 bits into DH, I have also overwritten part of DX, And I've also overwritten part of EDX because those DH, those are in there. So very, very cool. And then we could print that out. I'm going to do a $sign, DH, hex, and then I'll show you the trick. So is there a way to see it in decimal? And the answer is yes, there is. I'm running out of room. Well, not really. I'll just stretch. I don't know if anyone else has this problem, but I cannot grab the edge of this stupid screen ever. Come on. I don't know why. Can I grab the other edge? Give me a break. It was very difficult to get a handle on that window. Okay, so here's another trick. You're going to want it. You're going to see it again here in just a second. If you print a register like DH, you're going to get hex data because that is what HLA will do. If you want to see what it looks like as decimal, you can do a typecast on it in HLA, and you typecast it to one of the integer types, and HLA will show it to you in decimal. So in this case, it's an 8-bit register, so I'm typecasting it to an 8-bit data type. And an HLA data type, an integer data type, will actually cause HLA to show it as decimal. So you can have both. And then we can, instead of using the calculator, we can see what these 8 bits look like in DH. And then I see there's a question up, so I'll answer that in just a sec. So the value we put in DH in hex is AA, and in decimal, because of the typecast, is 170. That's sort of as we would understand that value, is 170. Now we can cheat and go type 170 in at the calculator, and in fact, that is what those 8 bits would look like. Okay. Yeah, so there's that. We'll come back to this idea, this typecasting idea, in just a moment. All right, so let me see. There's a question here. Yeah, so someone asked if we move a value that's too big for a register, will HLA error out? So let's try it. So if we move 256 to AL, that is not a value that AL can accommodate. AL can only go from 0 to 255. 256 is too big. So let's see what HLA does with that. So I get an error, and it's a good error in this case. They're not always good ones. This one's a good one. Constant is the wrong type, or too large for the specified register. That's at line 25. The near part is of no use to us, but HLA did recognize, wait a second, that constant value don't fit. So pretty cool. Okay, so there's not much good samples in there, but hopefully just some things to get you thinking. Move is a copy. You can do moves with decimal values or hex values or binary values in HLA. When you move / copy a value to a destination, they both have to match in size. When it comes to the decimal versions, it has to be something that is small enough to fit. So when you do a move with a decimal literal value, you have to kind of in your head imagine what it looks like in binary to understand whether or not it would be possible for it to fit. So if I go to my calculator, where is my calculator? And I put in 256, I'm going to notice that 256 requires 9 bits of storage. So nothing 8 bits could fit it. Now, if I were to use just 99, that fits in 8 bits, which means that it would also fit in 16, which means that it would also fit in 32. So part of this, the experience I hope that you seek for yourself is to kind of play around with this and get accustomed to the idea that the size of things has to match. The number of bits that you're copying with your move instruction needs to match the number of bits where you want to copy it to. Yes, so the question about whether or not we're going to use the sub and add instructions in here in this class, yes, we will use them and quite a bit. So we'll do a lot of math instructions in this class. Okay, so there's kind of the lecture-y bit. Let me grab the lab. And again, sort of when I get notes from people, then I worry that maybe I'm just kind of doing too much, that people get distracted by what I'm doing as in a sample. So I'm not performing the lab. I'm going to get the code so we can look at it together, and if I think there's a place where I can be of service to you and giving you some hints about it, I will do so. So here's all we're given for lab 3. Why it wants it to be C++, I don't know. All right, so it doesn't give us much. I know I have to take time doing this, otherwise I'll read about it in Canvas inbox. Sorry for that. The lab requirements. So let's switch views. And go read the requirements. Properly document your code. I just did that. Use a loop to allow the user to repeat the program. We did that last week. I'm not going to do it again this week. You have a sample for that. Okay. Read in for uns8 and store the input values in DL, CL, BL, and then AL. So I'm going to do 1 or 2 of those as an example to get you started on this. How do I read in an uns8? And then next I'm supposed to read in an uns16, and then finally an uns32. So at this point, what I want you to be thinking, when I see uns8, I should be thinking about the size of that thing and where things of that size could fit in terms of the registers. An uns8, that means an 8-bit unsigned integer. So I have 8 choices for where that could fit in the registers that we are using. AL, BL, CL, or DL. Also AH, BH, CH, or DH. Fortunately, the instructions tell me which of those 8 to use right here. Take the first input and put it in DL. Take the second one, put it in CL. Third one in BL. Fourth one in AL, and so on. Same for the next, and then display their contents in both hex and decimal. I mean, we need to typecast. Then we're going to do uns16s. So we should be thinking, all right, what register segments could I use to store uns16, since we're only using registers? AX, BX, CX, DX, although the instructions tell me to use those in reverse order, so I will do that. Then it tells me to display the contents of those 4 registers. Then it tells me to display the contents of the L, the low sections. The reason why it's doing that is because it is there sort of for you to learn by it that the process of writing data into AX, BX, CX, and DX necessarily affects AL, BL, CL, and DL. So if I write inputs into the AX, BX, CX, and DX, and then I view the L parts, I'm going to see changes there because I just wrote into those segments. So this is the second time in this lab that you will display those 4 registers. The second time you're doing it to observe for your own purposes the fact that those changes to DX, CX, BX, and AX were also changes to those L portions. The last section, uns32s, we're going to store in A, B, C, AX, EAX, EBX, ECX, EDX, and then we're going to redisplay the 16-bit segments to prove that altering the 32-bit segments alters the 16-bit segments, which also alters the 8-bit segments. So this will be the second time in the lab that we display those 16-bit segments, and the third time in the lab we will display the 8-bit segments, all of it so that you have an opportunity when you run your program and observe the results, can think to yourself, why did AL change when I put a value in AX? And why did AL change and AX change when I put a value in EAX? And can I see that on the screen in front of me? It's a lot of outputs, but it's not too bad. So Drew had asked, it's just kind of get to be a little bit of a mess. It's not too bad. I'll show you how I would do it in a sample real quick. It's a lot of data. And I promise you with the 50-ish versions of it that I have to go through and evaluate and test, that my experience is a lot more miserable for it than yours will be. So I am taking a hit for it, if it makes you feel any better. But also sort of consider that when you design your outputs to not be cruel. Okay, so we're about to switch over. I am starting to push it on time. Hopefully I switched the view back. Sorry, I did not. Let me switch back and let's look at this documentation real quick before I do a sample or two. So one of your readings is this page on the standard input module. And I'm just going to go show you the routines that we're going to use, and then we'll think about how they work. So we are going to be reading in unsigned 8-bit integer, unsigned 16-bit integers, and unsigned 32-bit integers. So I'm going to scroll down. I know roughly where to look. We don't want signed, we want unsigned integer routines. So here is the routine that we will use for reading in unsigned 8-bit integers. And it tells us that it has a return value. Now this is a trick because it's not actually a return value in the way that we often think of it. What it's actually telling us is that you will find your recently keyboard input 8-bit integer in the AL register. So that's what that means. If you call this routine, you're going to get a keyboard read value in AL. So we'll keep that in mind. We're going to use the get U16 to get the 16-bit ones for part 2 of this lab. And it tells us if you use this routine, you are going to find the input value in AX. Useful to note. That's the only place that we're going to discover that this is the case, by the way, is in this documentation or me telling you. And then the get U32 ones return a value in EAX, which really just means, hey, after you run this routine, that's where you go to find your input value. So let's see what that looks like in code now. Okay, this. I'm sure I'm supposed to do a greeting. That I'm not doing a greeting is not telling you not to do a greeting. I'm not going to evaluate this code. These are samples to help you get started. So the reason why I'm saying to 0 to 255 here, I'm not going to do any error checking on it. And if the person puts in 256, the program's going to crash. We will deal with that problem in a future lab. But the reason I'm putting that value in is because that is the range of values that an unsigned 8-bit integer can take. You know where to go, I hope, to figure out what the range for unsigned 16-bit values are. Hint, it's in Wikipedia and also all over the internet. And you also then know where to go to find the range of values you can store in an unsigned 32-bit integer. So we might call this part 1, unzade inputs. So standard in got get U8. That's the routine. I have to have read the documentation and made note of the fact that my value is sitting right now in AL. The lab tells me that this first input needs to be in DL. Well, that's simple then. I will simply copy the AL that my keyboard input is presently sitting in into DL, and I've accomplished that first task. What happens to AL in all of this? The same value is sitting there, but I'm also not going to be super clever with my user interface because I want to go faster. All right, so here's my second one. I call this routine. What happens to the first value that I input? It just got overwritten because AL just got overwritten with a brand new Don't forget those. They will cause pain somewhere. I just overwrote the initial input in AL with the new input. But I didn't lose AL. Why? Because I copied the first input into DL. It's safely sitting off to the side in a different register. And I'm going to do the same thing here. And now I'm going to do some copying and pasting for the third input. So the third input is also going to go into AL, which in theory would overwrite the second input, but I have already copied it over into another register in the order I was told in the lab, which was DL for the first input, done. CL for the second input, done. BL for the third input, done. And then the fourth input, AL. So there's all four inputs. I'll give you a moment. I know I'm going over a little bit. It's not going to be way crazy over almost at the end of this. So is there anything that anyone would change about my code? There's something in there that I really don't actually need. So Druid asks, is AL always the default 8-bit storage register? Not always, Druid. So the question of when is AL in play is based on, oh, you can't see it. Switch views. Why is AL constantly showing up this way? It's because the library routine for reading unsigned 8-bit integers is always using AL. So that's true. This routine always lands a value in AL. Not all routines will always use A or some part of A. We'll discover that by reading the library documentation. It is not the closest. It's just where the author of this library decided to put it. And they documented the fact that that's where they're putting it, so that's just all there is to it. You will find that the libraries in HLA favor the A register or some part of it over other registers much of the time, but that was the author's decision, and nothing else than that. So it doesn't have anything to do with it being closer to anything. It's just a register that the person who wrote the getU8 function decided to use to deposit the keyboard input into. Okay. Those are good questions to ask and to be thinking over. It will help get it clear in your head, I think, faster if you're asking, like, why is that? So it's a good question to ask and have answered. In this case, why is that? Because the author wanted it that way. And they tend to be fairly consistent. The author of our libraries, the HLA language, they tend to favor the A registers for stuff. Okay, so is there anything anyone sees in this program that doesn't seem like it's necessary? It's a lot of lines to look at, but there is one line in here that we could do without. Good one, Druid. So this line 27 doesn't hurt anything, and it will compile. But if the input is already where I want it, then I don't need to copy it anywhere. So getU8 puts the fourth input in AL. I was instructed to have the fourth input in AL, so I can just stop. Okay, now we'll do the 8-bit outputs. You've seen this. So now what we're instructed to do is do some outputs. I can't remember if I specified what they're supposed to look like. I would just say to give you what you need to figure it out. So AL, I'm just going to put a colon in there. $, AL for the hex, which is required. And I'm going to go ahead and label it because I think that that is just helpful to have that. Comma, and then to get it to look like decimal, we typecast it to uns8. So notice how the typecasting works. The whole thing is in parentheses. So in parentheses, you type, in this case, uns8. AL is what I want to see as decimal. So that highlighted section on the screen is how you take what HLA is going to want to show you as hex, which is a register, and forces HLA to instead show it to you as decimal, which HLA will do if you typecast it to an integer, because that's how HLA was designed to work. And then I'll label the other one. And again, just because I'm not doing them all doesn't mean that they don't all need to be there. Please read the requirements. I'm just, for the sake of efficiency, going to show you that one. So I'll just go 10, 20, 30, 40. Those are all between 0 and 255. And there is what AL ended up with, which in hex looks like 28. But it was the value 40, and that should be what it has in it, because the fourth input is supposed to be in AL. So I would probably even, do these in the order that they landed, because otherwise it would just be weird to not do so. All right, I'm already kind of offering quite a bit there. More, so that you get the idea. DL would be the first input. I numbered it. So part 2, uns16 inputs. I'm just going to put some notes here. You're going to need standard in.get u16. Part 2 is also going to have 16-bit outputs, and part 2 is also going to have 8-bit outputs. And again, that's so that you are kind of compelled to look at your program running and to think about why, when I am doing 16-bit inputs and storing them in DX, CX, BX, and AX, does that seem to have some effect on DL, CL, BL, and AL? I'm looking at it on my screen. Part 3 is going to have 32-bit inputs and then 32-bit outputs, another set of 16-bit outputs, and another set of 8-bit outputs. So you kind of see that it doesn't scale badly in terms of you can just keep reusing. Like I'll just repeat this same 8-bit outputs for part 2, and then I will repeat them again for part 3, and the same goes for the 16-bit. So there's that. Okay, I'm going to spend just a couple of minutes looking at the project, and then we will call it a day. Thanks for staying a little bit long, if you're staying a little bit long, if you were able to. So I'm not seeing any questions in chat about that. So we are, HLA-wise, we are experiencing how HLA will present registers to us, which it will use hex when it prints it, versus how HLA will present integer data types, which we are using typecasting to affect. I'll give you a hint down here on part 2. Hint, type uns16 and then for part 3, skipping over a part, of course, hint type uns 32 BEBX, just as an example, will appear. I shouldn't say once, but that is true. So to give you a hint about the typecasting for the different sections. So that's from the HLA perspective. Registers are going to print on the screen as hex. And you need to be careful that you're showing that in your output so that you and I don't get confused. If you use this typecasting trick, then you can get HLA to convert the register data into integer types, which in HLA means decimal types. Notice there are no variables. This lab does not need any variables. It doesn't want any variables. Using variables is just extra code and a waste of your time. So why use them if you don't need them? This will be my little sort of Easter egg to see who watched, I guess, the video. Okay, so hopefully that is plenty enough to get you started on lab 3. I guess I'll post that. In the sample so that you have that to refer to, as much good as it seemed to do last week. Yes, Evan asked, can you make functions in HLA? And you can. The HLA word for a function is a procedure, and we will be writing them in the next several weeks. So HLA supports functions. It also supports classes, as it turns out. We will not use those. But we will use procedures, and we will create them in class. Okay, real quick, 2 seconds on the project. I'm going to go back to the home page. You need to be able to see that. So let me go back to the home page for the class. Scroll down to the schedule, which is a quick way to get to the project. The modules in the reminders page will always link to the nearest project as well. So individual project 1. It's not anything fancy. It's a vending machine of sorts. So many of you have written something like a vending machine. This is a ways out yet. We have half the semester, but the time to look at it and know what's coming lies in the future. What we will do assembly-wise in the vending machine, we won't actually be doing any register stuff unless you want to. But you'll be doing a lot of arithmetic at the assembly level. So the big part of what the first individual project is about is giving you a chance to practice and demonstrate your mastery of x86 arithmetic instructions like add and sub that came up today. And then just some sort of generalized programming practice using the HLA language. So I have to do another Linkage asks, I can't, I got to do a whole bunch of video moving around, and then I got to do another stream here. So I'll be off for a while I'm doing that and preparing for my next class. Okay, so that's it for the week. I will post, I don't think there's anything useful in the week 3 sample, really. All of that stuff is kind of repeated in the lab sample that I set up. So I'm just going to post the sort of helper tips for the week 3 lab to the lecture page, and that's it for this week. So yeah, that's where we'll leave it. You can use Canvas Inbox if you have questions for me. If you have programming, if you get hung on a programming issue, it's super helpful if you put it in Piazza and kind of give more of us a chance to help you and also to see what is likely to be a problem that many of the rest of us will encounter. So that's a great place to go with, I don't know what to do with this part of the lab kinds of questions. Questions about scoring and stuff, of course, Canvas Inbox is a good place to do that. And I can address your questions there about scoring. Anyway, I'm going to call it the end there. Rest my voice for a while before I do my next class. Have a good week. I look forward to seeing you next week. We're starting to do stuff that's fun to do, at least in my opinion. Hopefully you find some of it fun to do as well. And I'll see you on Tuesday next week. Take care.